have a son who is a computer gamer, and he gets very passionate about when he gets a new game, ranking up to different levels. And I decided in this webinar, what I was going to do was we're going to play a game. So we're going to rank up to different levels. I've got 8 levels. So we've got this brand new game that we're going to start with the basics. We're going to learn how to play this game, and we're going to see how we go as we go along. So I've got 8 different levels, and we're going to see how far we can rank up. I believe that's the correct terminology. I think it's important with counting principles that you don't just tell your learners, draw slots, write down numbers, put a time sign between, and you get your answer. Because then they won't understand what they're doing and why they're doing it. So starting with a question something like this, now this you can ask very easily in grade 7. So there's no reason why you can't do an introduction to counting principles from a very early age. A dog runs through 2 fences. One has 3 holes and the other has 4 holes. How many different ways can he run through the 2 fences? Now we know exactly what to do. We know 3 holes, 4 holes, 3 times 4 is 12. But do your learners know why that is the case? So I would suggest in the beginning, you go slowly and you actually get them to work out exactly where they could go. So if I number the holes A, B, C, and the other fence 1, 2, 3, 4, your dog can go A1, A2, A3, A4, or B1, B2, B3, B4, or C1, C2, C3, C4. Now, if you're doing this with grade 7 or grade 8, you actually need to get them to list all the ways, and then you can say to them, what would be a quicker way of doing this? With the grade 12s, I would get them to start maybe listing it and saying, okay, so if the dog runs through hole A, how many options does he have? Well, there are 4, because it could be A1, A2, A3, A4. If the dog runs through hole B, there are also 4 options. If the dog runs through hole C, also 4 options. So I've got 4 options plus 4 options plus 4 options. And what's a quicker way of doing 4 plus 4 plus 4? Well, it's 3 times 4. So you're slowly developing why is it 3 times 4. If I take a second example, at a restaurant, there's a choice of 3 starters, mushrooms, soup, or pate. 4 main courses, chicken, beef, fish, vegetarian, and 2 desserts, ice cream or trifle. How many different combinations could be chosen? And again, this can very easily be asked at a grade 7 level. So if we start by listing everything, well, if you have mushroom and chicken, then you could have ice cream or trifle. So mushroom, chicken, ice cream, mushroom, chicken, trifle. If you have mushroom beef, then you can have mushroom beef ice cream or mushroom beef trifle. If you have soup with the chicken, we're sticking with mushroom with the fish, then it could be with the ice cream or the trifle. Mushroom with the vegetarian, it could be with ice cream or trifle. So mushroom and chicken, there were 2 options, ice cream or trifle. Mushroom and beef, there were 2 options, ice cream or trifle. Mushroom and fish, 2 options. Mushroom and vegetarian, 2 options. In other words, we've got 2 with the chicken, 2 with the beef, 2 with the fish, 2 with the vegetarian. So that's 8 different options. But what about if you start with soup? What's exactly the same process? Soup and chicken, there are 2 options. Soup and beef, 2 options. Soup and fish, 2 options. Soup and vegetarian, 2 options. So another 8 from the soup. What about with pate? Exactly the same thing. And I think, obviously, depending on the learners you're teaching, will determine how quickly or slowly you can go through this. And I think very easily they can see there are 8 options with the mushrooms. Where did that come from? Well, there are 4 choices of mains and 2 desserts. And then there were 8 with the soup and 8 with the pate. And very quickly, I think you can get to the fact that there are 3 options here, 4 options here, 2 options here. 3 times 4 times 2, 24 different combinations. What about this? You're offered ice cream at a party. You're allowed 2 scoops of ice cream on a cone. The flavors available are vanilla, chocolate, strawberry, peanut butter, blueberry, and lemon. Sorry for all the food if you're hungry. How many different combinations can you make if you firstly have to choose 2 different flavors and secondly are allowed to have 2 scoops of the same flavor? Now, we've got to be a bit careful with this one. In probability with the dice, where I said to you that throwing a 1 and a 2 on 2 dice is very different to throwing a 2 and a 1. However, in this question, if you have vanilla and chocolate on your ice cream, it's exactly the same as if you have chocolate and vanilla. I haven't said to you vanilla at the bottom, chocolate on the top, or chocolate at the bottom, vanilla on the top, because those are different. I've just said you are allowed 2 scoops of ice cream on a cone. So vanilla chocolate and chocolate vanilla are the same. How many different combinations can you make if you have to choose 2 different flavors? If you are allowed to choose 2 scoops of the same flavor as well. Okay, again, you can ask this to grade 7. And grade 7 level, I would make them list everything. So vanilla with chocolate, vanilla with strawberry, vanilla with peanut butter, vanilla with blueberry, vanilla with lemon. And there I've got them there. So there are 5 possibilities. What about chocolate? Well, I can't have chocolate and vanilla because that's the same as vanilla and chocolate. So now I can have chocolate with strawberry, chocolate with peanut butter, chocolate with blueberry, chocolate with lemon. So that's another 4. Strawberry, don't go backwards because I've got those already. So it's strawberry, peanut butter, strawberry, blueberry, strawberry, lemon. And then I've got the other ones as well. So I've got 15 different combinations. So for those of us who know about counting principles, what choices do I have for my first scoop? There's 6, because there's 6 flavors. How many choices do I have for my second scoop? There are 5, because I said it had to be 2 different flavors. 6 times 5 is 30. But I'm getting 15 different combinations. So how do I match the counting principles that we know with the answer I'm getting here? Well, I need to halve it, because a scoop of vanilla and a scoop of chocolate is the same as a scoop of chocolate and a scoop of vanilla. So I need to halve that. A little bit like the handshake questions. You know, if you've got 7 people at a party and everyone shakes hands with everybody else, how many handshakes are there? Well, that's 7 times 6 divided by 2. And we divide by 2 because my shaking hands with you and you shaking hands with me is exactly the same handshake. So what about 3.2? If you now are allowed to have 2 scoops of the same flavor, so it's all these 15 as well as vanilla, vanilla, chocolate, chocolate, strawberry, strawberry, and so on. So 6 more, so 21. But how am I getting that using counting principles? Well, if you think of rolling a dice, which we did on Tuesday, when you draw up a table of all the options when you roll a dice, you had 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Now that's the same as vanilla, chocolate, the 6 flavors and the 6 flavors here. With this one, so you get 36 possibilities. With this one, the 3.2, I am allowed 2 scoops of the same flavor. So I am allowed vanilla, vanilla, chocolate, chocolate, strawberry, strawberry. In other words, that diagonal. So we exclude that diagonal. So I've got 36 possible combinations minus the 6 on the diagonal, which is 30. The triangle I get at the top and the triangle I get at the bottom are duplicates, just the other way around. So the vanilla, chocolate, chocolate, vanilla are just the other way around. So I exclude either the triangle at the bottom or the triangle at the top, because I can only have one of those, because I can't have duplicates. And that's where I'm getting the 15 from. But then I add my diagonal again, which I'm allowed. And that's where the 21 is coming from. So it is sort of using counting principles, but I need to think. Question 4. Sorry, again, a food one. You've got the following items on a menu. You've got 3 starters, 4 mains, 2 desserts. Now we've got into realizing, okay, so I can take? How many different meal combinations are there? There are 3 starters, there are 4 mains, there are 2 desserts. So it's 3 times 4 times 2, which is fine. And there I've got that there. The second question, how many different meal combinations are there if a person wants to eat chicken? So just have a look carefully. You've got grilled chicken and curried chicken here. So there are 2 options in the mains where you can have chicken. So now it is 3 times 2 times 2, which gives you 12. So what we've done here is we've taken an introduction to counting principles with very, very practical questions where you can list them all to make sure. And then you can see, okay, how do I get from mushroom chicken malva, mushroom chicken ice cream, mushroom mince malva, mushroom mince ice cream? How do I get from listing it all to getting an answer quite quickly? Because as you know from the counting principles questions, there is no ways I'm going to be able to list them because our numbers go into millions. We've ranked up. We're on the bronze level. We're now at the second level. We're now ready to start counting principles, but we're still going to go slowly because we're still just learning this game. Question 5. The digits from 0 to 9 are to be used to make a 10-digit code. Determine the number of ways to do this, given that the digits may be repeated, the digits may not be repeated. So we need to start slowly with our learners because, of course, the repeating and the not repeating comes in all over the place. How I suggest we do this, you get your learners to draw 10 slots. I know in the beginning it takes a long time, but for them to realize what's happening, you want a 10-digit code. So you draw 10 slots. How many choices do I have in this first slot? Well, I can use the digits from 0 to 9. Now be very careful. 0 to 9 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 digits I can use. So how many digits can go into my first slot? 10. The digits may be repeated. How many digits can go in my second slot? 10, 10, 10, 10. In other words, how many possible codes can I make? It's 10 times 10 times 10 times itself 10 times. In other words, 10 to the power 10. And depending on whether you're British or American, that's either 10 trillion or I'm not sure, 10,000 million, but it's 10 with a huge number of zeros. And that's why I say to you, these numbers are just crazy. So that's if the digits are repeated. If the digits are not repeated, again, draw 10 slots. You're using the digits 0 to 9. How many digits can go in the first slot? 10. Once I've used that digit, I can't use it again. So how many digits can go in the second slot? Only 9. And then 8, and then 7, all the way down to 1. And what do I do to those numbers? As we saw with the simple examples with the dog and with the food and with the ice cream, we multiply them. So 10 times 9 times 8, all the way down to times 3 times 2 times 1. And that we have a notation for. We call it 10 factorial. Use a calculator to work it out, and you get 3 million, etc., etc. Again, a very large number, but nowhere near as big as when the digits were repeated. Okay, so what happens if we take question 6? We're still using the digits 0 to 9, being used to make the 6 a 6-digit code now. So the previous question was a 10-digit code. This is a 6-digit code. I said we're ranking up, but we're still going slowly in the beginning. Determine the number of ways to do this, given that the digits may be repeated and the digits may not be repeated. So exactly the same question as the previous one, still with the same number of digits, but now we're doing a 6-digit code. 6 slots. If the digits may be repeated, again, 0 to 9 is 10 digits. So again, it's going to be 10 times 10 times 10, 6 times. In other words, this is now 10 to the power 6 because there are only 6 slots in this question. What about if the digits may not be repeated? Well, how many numbers can go in the first slot? 10. I've used a number, so in the second slot, there are only 9 available. Then 8, 7, 6, 5. So it's not a factorial. I know you can do it with factorials if you end up dividing and all sorts of things, but it's not a straightforward factorial. So I wouldn't teach my learners that. I would just stick with the slots. It's 10 times 9 times 8 times 7 times 6 times 5. Why is it no more? Because this is a 6-digit code, not a 10-digit code. Use a calculator, get your answer. Question 7. Determine the number of ways the letters of the word manna can be arranged. Now you will notice manna has no duplicate letters. Again, I'm going to use slots. There are 5 letters here, so I'm going to use 5 slots. So they're my 5 slots. How many letters can go in the first slot? 5. It could be M or A or N or O or R. Now, I don't need to say anything about repeating or not repeating because you've been given 5 letters. Once I've used a letter in that first slot, I can't use it again. So how many letters are possible in the second slot? 4. And then 3 and 2 and 1. And it's 5 times 4 times 3 times 2 times 1, which is the same as 5 factorial. Use a calculator if you're not sure, and you get 120 for that. Okay, what about question 8? Very similar question. Determine the number of ways the letters of the word equations can be arranged. A longer word, 9 letters. Still no repeats. And interestingly, it's a mathematical word that uses all 5 vowels, which is just a random thing. Okay, so if we take it, 9 slots. How many letters can go in the first slot? 9. Once you've got a letter there, I can't use it again. How many letters in the next slot? 8, 7, all the way down. In other words, what have I got? I've got 9 factorial, a large number. Okay, let's keep going. Question 9. There are 16 teams playing in the Netball World Cup. The flags from each country are to be flown in a straight line. Determine the number of ways this can be done if, firstly, the flags may be in any order. Secondly, the South African flag has to be flown first, as we are the host nation. And then thirdly, New Zealand's flag is flown first as the previous champions, then South Africa as the host nation, and then the others in any order. Now, the problem with trying to get a relevant question, because this was the Netball World Cup, which was a few weeks back, there were 16 teams playing. The problem is if you have 16 flags, these numbers are massive. Because as you know, the factorials, the bigger the number goes, the more, the more the answer goes. So to try and get, relative and real life and all that kind of thing, your numbers go incredibly large. So it might be better for a test or an exam just to sort of have it as a small round robin tournament is done or something like that. So if we look at it, the flags can be flown in any order. How many can go in the first slot? 16 times 15 times 14, all the way down to 1. So it's just 16 factorial, which is too big for my calculator. So I'm in scientific notation, which is also something one needs to discuss with learners just in case they do give them something that is really, really large. If the South African flag has to be flown first, then how many flags can go in the first slot? Only 1, our flag. How many flags can go in the second slot? 15. Because our flag is flying first, there are 15 left, times 14 times 13, all the way down to 1, which is basically 1 times 15 factorial, which is still a very large number in scientific notation. When I get to New Zealand's flag being flown first, how many flags can go in the first position? 1. Then South Africa is the host nation, 1. And then they can be in any order. So 14 times 13, all the way down to 1. So it's 1 times 1 times 14 factorial, which is still too big for my calculator. Okay, the warm-up question. For those of you who were with us in the beginning, a code is made up of 3 letters followed by 3 digits. Any letter may be used, but they may not be repeated. Any digit may be used, and they may be repeated. How many such codes are there? So, how many slots do we need? We've got 3 letters followed by 3 digits, so we need 6 slots. Any letter may be used. Another thing that you need to make sure your learners know is that there are 26 letters in the alphabet. So any letter may be used. So how many can be in the first slot? 26. Letters may not be repeated. So how many may go in the second slot? 25. So they're my 6 slots. 26 in the first slot. Only 25 in the second slot because I may not repeat letters. 24 in the third slot because I can't have the same as I had in the first 2. Then it was followed by 3 digits. Any digit may be used, which means I've got 10 possibilities. They may be repeated. So it's times 10, times 10, times 10. So now we're starting to get some conditions with it. So it's not just straightforward 10 times 10, however many there are. It's not just straightforward 10 times 9 times however many. It's not a straightforward factorial. I've got part of it not being allowed to repeat, part of it being allowed to repeat. But the principle still remains the same, where I see how many do I have in each slot, I multiply them, and again, I get a big number. Okay, question 10. A code is made up of 3 letters followed by 3 digits. So very, very similar question. Only consonants may be used. What's a consonant? Well, the alphabet, our alphabet, the English alphabet, which is the one that we use. And in fact, it's not only the English alphabet, but certainly there are many alphabets in the world that are very different. So we need to make our learners know that the alphabet we're dealing with is basically A to Z, where there are 21 consonants and 5 vowels. They need to know that the vowels are A, E, I, O, U, because that's going to come into questions as well. So only consonants may be used and they may not be repeated. Any digit from 0 to 6 may be used. They may be repeated. How many such codes are there? So very similar to the first question, 3 letters, 3 digits. But now I don't have the full alphabet. I've eliminated 5 letters. Still may not repeat letters. I don't have all the digits. I've got 0 to 6. How many digits are from 0 to 6? There are 7 of them. 0, 1, 2, 3, 4, 5, 6. Okay, there's 7 digits and they may be repeated. So it's a very similar scenario, but just I've got to have different numbers. So 6 slots I need, 21 consonants in the alphabet. So 21 for the first slot. May not be repeated. So 20. May not be repeated. So 19. The digits 7 because it's from 0 to 6. So 7 may be repeated, 7, 7, and there I get my answer. So there's question number 10. Question number 11. A code is made up of 3 letters followed by 3 digits. Same thing. The first letter must be a vowel. Thereafter, any letter may be used. Okay, any letter. So it doesn't say anything about I can't repeat. Any letter may be used. Any digit from 0 to 9 may be used, but the last digit must be even. Okay, doing a Google search, many sites told me that 0 is counted as an even number, which I was interested to see because, of course, when we asked the grade 8s, list the first 5 even numbers, they give us 2, 4, 6, 8, 10. But when we're talking about digits being even, 0 is an even digit. Okay, how many slots do I have? 3 plus 3, 6. The first letter must be a vowel. So how many letters can go in the first slot? Well, how many vowels are in the alphabet? 5. Thereafter, any letter may be used. How many letters are left? 26 and 26. Okay, so let's actually start looking at our solution. 6 slots. First slot has to be A, E, I, O, or U. So there are 5 possibilities. The next slot, I may use any letter. Doesn't say I can't repeat. I may use any letter. So 26, 26. What about these 3 digits on the end? The last digit must be even, which means the last digit has to be 0 or 2 or 4 or 6 or 8. So there are only 5 options for that last number. But the other 2 digits, any digit may be used. So I get a 10 and a 10. And of course, once you've got the numbers in the slot, the rest is easy because, as we've discovered, you just multiply them and you use your calculator to get your answer. The difficult part is working out what numbers go into the slots. We're on the silver level. We have ranked up. So we've done the first 2 basic levels. Things are going to get a little more complicated, but not hectically yet. Unfortunately, when I look at past matric papers, both provincial and national, which level do most of the counting principles fall into? Unfortunately, they mostly fit into our 7th level. That's got nothing to do with the level 1, 2, 3, or 4 with cognitive levels. It's just got to do with the way I've designed this webinar, where I'm trying to take you from simple questions, getting the understanding of why we're doing things, making it a little more complicated, a little more complicated, a little more complicated, and so on. Okay, so let's get going in the silver level. The letters of the word pandemic are arranged in order. Pandemic, again, has no repeated letters, so I haven't touched any repeated letters yet. Determine the number of unique arrangements that can be made. That's fine, that was part of the previous level. Determine the number of arrangements if each word must start with C and end with M. So I'm starting to get some conditions coming in. And then 12.3, determine the probability that each word starts with C and ends with M. So we need to make absolutely certain, have they asked for the number of arrangements or the probability? It kind of brings back to mind the Venn diagram questions we were doing on Tuesday. Did they ask for the number of learners or the number of people in each category, or did they ask for the probability? And we know what to do with each of them. We've just got to make sure that we're answering the correct question. Okay, my first question is straightforward. Determine the number of unique arrangements that can be made. There are 8 letters here. So how many letters can go in the first slot? 8. How many in the second slot? 7, 6, all the way down to 3, 2, 1. So it's just 8 factorial is the number of unique arrangements of those 8 letters. I cannot repeat letters. So I've got 8 letters. I need to use all 8 letters. The second one, determine the number of arrangements if each word must start with C and end with M. Now, we also need to make sure that our learners know that when we say word, that doesn't mean they have to be a word in any particular language. They simply are arrangements. They are words that can be formed that aren't actual real words. They count as words because, yeah. So we need to make sure they understand that. So I've got 8 letters, 8 slots. Must start with C. How many C's do I have in the word? Only 1. It must end with M. How many M's do I have in the word? Only 1. How many slots have I got left? 6. What are those 6 slots for? Well, they're for the 6 letters that I haven't used. They're for P-A-N-D-E-I. How can I arrange those 6 letters? Well, they haven't told me any conditions on them. So how many letters can go in the first slot? 6. Then 5, 4, 3, 2, 1. So the number of arrangements is 1 in the first slot. 6 times 5 times 4 times 3 times 2 times 1. I can write quickly as 6 factorial times 1 in the last slot. So that gives me the number of arrangements starting with C ending with M. 12.3, if I go back, said to you determine the probability that each word starts with C and ends with M. Well, it's the same as the previous question. The previous question was the number of arrangements. This is now the probability. How do I get probability? Well, it's the number of successful arrangements divided by the total number. So how do I get my answer? Well, 720 is the number of arrangements starting with C, ending with M. 40,320 was the total number of ways I can arrange these letters, which means what is the probability? It's that over that, which is 1 over 56. I can do this a different way. And for those of you who were with us on Tuesday afternoon, I had a question that I said to you there. It looked like counting principles, but we could actually do it without. And this is another one. If we think of the word pandemic, what is the probability that it starts with a C? Well, how many C's are in the word pandemic? 1. How many letters are in the word pandemic? 8. So what's the probability that a word starts with C? It's 1 over 8. What is the probability that a word ends with M? Well, how many M's are in the word, bearing in mind that the C is gone already? There's 1 M in the word. How many letters are in the word, bearing in mind that the C has gone? There's 7 left. So the probability of starting with a C is 1 in 8. Probability of ending in an M is 1 in 7, because the C is already in the beginning. There are now 7 letters left. So what's the probability? It starts with a C and ends with an M. It's 1 over 8 times 1 over 7, which is 1 over 56. Same answer. Which way is better? I don't know. In this one, probably because you had these 2 answers already, because I led you into it slowly, probably the first way is the quicker one, because I've got the 2 answers, but there might be others where the second way is a quicker one. And we're going to do a number of examples that look like this. Okay, so the second question, for those of you who were with us in the beginning, before we started, consider the word hexagon. If the letters are randomly selected and all the letters are used, determine the probability that the word will start and end with a vowel. Okay, it's probability. It's in counting principles. Do I use counting principles? Do I use probability? I don't know. We're going to use both, and you decide which you would prefer to use. So we've got 7 letters. There are again no duplicate letters. Okay, no duplicate letters are coming in yet. What's the probability that the word will start and end with a vowel? Okay, if we do it with counting principles, there's 7 letters. What is the total number of ways of arranging 7 letters? 7 factorial. Now it must start and end with a vowel. How many vowels do I have? E, A, O. So how many letters can it start with? 3. How many can it end with? 2. Okay, so let me get my solution. So the total number of arrangements is 7 factorial. Vowel at the beginning and the end. So it's 3 in the beginning, 2 in the end. So it's 1 letter out of E, A, and O. It's another one out of whatever's left that I didn't choose in the beginning. How many letters are left? Well, there's 7 letters in hexagon. I've used 2 already, so now I've got 5 left. How many ways can I arrange these? 5 factorial. So how many ways can I have a vowel at beginning and end? It's 3 times 5 factorial times 2. So what's the probability? It's 720 divided by 5040, which is 1 over 7. So there's one way of doing it. If I look at it with probability, how many vowels do I have? 3. How many letters do I have? 7. What's the probability it starts with a vowel? 3 over 7. What's the probability that it ends with a vowel? Well, once I've put a vowel in the first space, how many vowels have I got left? 2. How many letters do I have left? Bearing in mind that 1 is gone in the beginning already, there's 6. So the probability that it will end with a vowel is 2/6. So what's the chance that it starts and ends with a vowel? Is 3/7 times 2/6. Same answer. And if I look at these, how did I get this one? I did 3 times 5 factorial times 2 divided by 7 factorial. Well, 7 factorial means 7 times 6 times 5 times 4 and so on. So I can write 7 factorial as 7 times 6 times 5 factorial. And when I take this divided by that, the 5 factorial in here will cancel with that 5 factorial. So I'm left with 3 times 2, and I'm left with the 7 times 6. What have I got here? I've got 3 times 2 times 7 times 6. So that's why your 2 answers are giving you exactly the same thing. Now, you must decide which way you want to teach it. I think if you've got strong learners, I would teach them both ways and let them decide which they want to do. I am a pessimist when it comes to counting principles. I doubt myself all the time. The others can tell you, when we do the matric paper at the end of the year, the 2 sections I want to know, what answer did you get? It's finance and counting principles. Because the rest, I either feel confident I've managed to do it, or I'm bleak because I really don't know what I'm doing and I don't know how to do it. And in fact, if I think 2020, that terrible COVID year when we all hoped the paper would be nice and we had one horrible finance question at the end, and we had Harry and the darts or the bullets or whatever it was, and it was the sum to infinity and whatever. That one I couldn't do either. So with counting principles, either I can't do them or I want to know what answer did you get because I need to check. So for me, I do both methods, because if I get the same answer, then either it's right or I've made a double mistake, which hopefully is unlikely. Okay, question 13. The letters of the word algorithms are used to form different 5-letter words. So now I've got a 10-letter word, but I'm only making 5-letter words. I am still not repeating letters. Okay, I'm not repeating any letters. So how many different 5-letter words can be formed? How many different 5 letters can be formed using only one vowel? Okay, slots. And I do slot all the time. So they're my slots, 5-letter words. Even though it's a 10-letter word they gave you, we're only making 5-letter words. How many different 5-letter words, how many different letters can go in the beginning? 10, because they're 10 there. How many can go in the second slot? 9, 8, 7, 6. It's not a factorial. So it's just 10 times 9 times 8 times 7 times 6. Use a calculator. How many different 5-letter words can be formed using only one vowel? Now, there's a quicker way of doing it than doing all of these. But in the beginning, I would go slowly and pedantically. The vowel could be first. How many vowels are there? There's A, there's O, there's I. So there are 3 vowels I can have in the first space. I had 10 letters. I can only use one vowel. So I had 10 letters, 3 of them are vowels. I've used one of them already. How many are left? 7. So how many letters can go in the second slot? 7, then 6, then 5, then 4. That's if the vowel is in the first slot. What if the vowel is in the second slot? Then I've got 3 ways in the second slot. The first slot has to be a consonant, so 7, and then 6, 5, 4. What about if the vowel is in the third slot? And if you're seeing something happening here, then of course get to your answer straight away. But if you're not, keep going slowly. Vowel in the third slot. There's my 3. 7, 6, 5, 4. Vowel in the fourth slot. 3 possibilities there. and so on. Vowel in the fifth slot, 3 possibilities, and so on. And I've written it out all the long way. It's 3 times 7 times 6 times 5 times 4 if it's in the first slot. 7 times 3 times 6 times 5 times 4 in the second slot, third slot, fourth slot, fifth slot. But when you multiply, what do you know about all these terms? Well, they're all going to give you the same answer, because when you multiply, it doesn't matter what order you multiply them in. So it's exactly that times 5. And once you realize that, you don't need to write this all out, which takes a while. But if your learners are not sure, or if you are not sure, write it out. You can see exactly what's happening with it. Why is it 3 times 7 times 6 times 5 times 4 times 5? And it's times 5 because the vowel could be first or second or third or fourth or fifth. And I get my answer. Question 14. A code consists of 3 digits, excluding 0, followed by 3 letters, excluding the first 6 letters of the alphabet. So again, I'm taking combinations of digits, letters, and I'm taking excluding certain things and so on. The digits and the letters may be repeated. How many codes can I make? Calculate the probability that the code starts with 7 and ends with T. Calculate the probability that the code has exactly 1 Q. Okay, so I think we can start going a little more quickly. 3 digits, excluding 0, so they're 9. Okay, I may repeat, so it's 9 times 9 times 9. Letters, excluding the first 6, 26 letters in the alphabet, minus the first 6 is 20. I may repeat them, so 20 times 20 times 20. So that's it. Probability that the code starts with 7, ends with T. Okay, so I've got 6 things. All right, it must start with 7. So how many options? 1. I can have any digit because I can repeat, but they said no 0, so it's 9 times 9. Must end with a T, so 1. I cannot have the first 6 letters, which means I've got 20 letters of the alphabet. I can repeat letters. So that was 1 because of the 7, 1 because of the T. I can repeat the digits, but no 0. I can repeat the letters, but no first 6 letters. Probability they asked for. So it's this answer divided by the total number. Another option starts with a 7. Probability, there's 1 7 out of 9 letters. Why only 9 letters? Because there's no 0. Ends with a T, 1 letter out of 20 letters. Why 20? Because I can't have the first 6 letters. Multiply, same answer. The last one, probability that the code has exactly 1 Q. Okay, says nothing about the digits. And this is in 14.2. This is 14.3. So the 7 and the T have fallen away. They've gone. They're not part of this question. So this question just belongs to my scenario at the top. So it has exactly 1 Q. All right. So my 3 digits, 999. The Q could be first, and then I can't repeat the Q. So there are 19 letters left, 19 letters. The Q could be second, which is why I've got 19 times 1 times 19. The Q could be third, which is why I've got 19 times 19 times 1. And again, I can do it as, 9 times 9 times 9, because the digits are doing nothing, times 1 times 19 times 19, times 3, because 1 times 19 times 19, and 19 times 1 times 19, and 19 times 19 times 1 is the same. Probability, so it's divided by the total number of codes. And to me, I'm sorry, that's a horrible number. So it's one of those, am I right? Am I not right? Did anybody else get the same answer? Because that's pretty yucky. So, but that's the nature of counting principles, I'm afraid. Okay, consider the digits 1 to 8. How many digit numbers can be formed if digits may be repeated? How many 4-digit numbers can be formed if digits may not be repeated? And then how many numbers between 3,000 and 4,000 can be formed? Now, With this one here, they haven't said you can repeat digits or not, but they're talking about numbers between 3,000 and 4,000. In other words, they're talking 3001, 3002, 3003, 3004, all the way up to 3,999. So they're talking actual numbers on a number line, which means you are repeating digits. So they're not going to, they don't specify it, but you can repeat. Okay, 2-digit numbers. I'm dealing with 1 to 8, so that's 8 numbers. I may repeat 8 times 8, 64. 4-digit numbers. I may not repeat, and I think we're getting this now. 8 times 7 times 6 times 5, get your answer. How many numbers between 3,000 and 4,000? Okay, between means not including. So how many numbers can start? Only one, a 3. I can't have a 4 because it's between 3,000 and 4,000. So I can only have one number in the first slot. How many numbers in the second slot? 8, because my digits are 1 to 8. 8, 8. Because I can have, well, I can't have 3,001 because it's no zeros, but basically I can consider 3,001 to 3,999, which means I can have repeated digits. Our 4th level. We've now hit gold. Okay. I'm afraid that means in that one thing, the questions are going to get more difficult. But as I said, the reality is that's what they ask. So we've got to get more difficult questions coming in. Question 16. Mr. and Mrs. Brown and their 4 children line up for a photograph. In how many ways can they line up if anyone may sit anywhere? That's easy. We've done plenty questions like that. In how many ways can they line up if Mr. and Mrs. Brown must sit at each end? That's okay, because we've done starting with this letter, starting with that letter. In how many ways can they line up if Mr. and Mrs. Brown must sit next to each other in the middle? So this is now a new thing coming in. In how many ways can they line up if Mr. and Mrs. Brown must sit next to each other anywhere? So there they're forced to be in the middle. Here they can be anywhere. Okay, let's have a look at it. They can line up, anyone may sit anywhere. How many in the first chair? 6. Second chair, 5, 4, 3. So it's 6 factorial. In how many ways can they line up if Mr. and Mrs. Brown must each sit at an end? Get your 6 slots. How many people can go in the first slot? 2. Either Mr. Brown or Mrs. Brown. How many people in the last slot? Only 1, because whichever of the parents sat in the first slot can't sit in the end slot. So 2 of them, either Mr. or Mrs. in the first slot, 1 in the last slot, it's the other one. The children, they say nothing about the children. So how many children can go there? 4 of them. Once that child is sitting, 3, 2, 1, and I get my answer. Okay, here are my 6 slots. Mr. and Mrs. Brown must sit next to each other in the middle. So that must be Mr. and Mrs. Brown. Child, 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 child. How many children can sit the end slot? 4. Once a child is seated, how many can sit there? 3. How many people can sit here if it's got to be either Mr. or Mrs. Brown? 2. It's either Mr. or Mrs. How many people can sit here? Only 1, because one of the parents has already sat in a chair. So that's the other one. This is a child. How many children have I got left to sit in chairs? 2. That's a child. How many children are left to sit in a chair? 1. So it's 4 possibilities, 3 possibilities, 2 there, not because I'm doing a factorial, but because this is Mr. or Mrs. Brown. 1 there because it's the other one of Mr. or Mrs. Then 2 because there are 2 children left, and 1. Now, this one here, in how many ways can they line up if Mr. and Mrs. Brown must sit next to each other anywhere? Now, I haven't put them with slots because they can sit anywhere. But what I have done is I've put Mr. and Mrs. Brown in a box. So Mr. and Mrs. Brown are holding hands. They're glued together. You can't separate them because they've got to sit next to each other. So I now think of arranging the parents, child 1, child 2, child 3, child 4. So how many things am I arranging? 5. I'm arranging 5 things. In how many ways can I arrange 5 things? 5 factorial. But Mr. and Mrs. Brown, they're holding hands, but they themselves can either sit Mr. and Mrs. or Mrs. and Mr. So they can arrange themselves in 2 factorial ways. Now, I know 2 factorial is the same as 2, but when it comes to 3 things, 3 factorial is not the same as 3. So we need to make sure our learners know that while Mr. and Mrs. Brown, there are 2 ways of arranging it, it's actually, you've got to consider it as 2 factorial ways. So there are 5 things I'm arranging. Parents, child, 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 child. 5 factorial. Times 2 factorial, because Mr. and Mrs. Brown can go either way. Question number 17. Consider the word boundary. They still are all different letters. Don't make things too complicated too quickly. So don't just leap into, no, we need to do lots and lots. Okay. What have we got here? Similar to the Browns. How many ways can you arrange the letters so that the vowels are always together? What vowels have I got? O-U-A. Think of O-U-A as one group. So they're in one group. And then I've got B-N-D-R-Y. So how many things am I arranging? The vowels, B-N-D-R-Y. I'm arranging 6 things. How many ways can you arrange 6 things? 6 factorial. However, the vowels, there are 3 of them. How many ways can I arrange 3 letters? And that's why it was important to do the factorial. It's 3 factorial ways. So you think of those vowels as one group, one unit. There are 5 consonants which are all separate. There were no conditions. So it was a unit of vowels plus 5. That's where the 6 factorial comes from. The 3 factorial comes because I can arrange the 3 vowels in 3 factorial ways. Question 18. Okay, 5 maths books, 3 science books are to be placed on a shelf. The books are all different. In how many ways can they be arranged? In how many ways can the books be arranged if the 5 maths books must be together? In how many ways can the books be arranged if the maths books must be together and the science books must be together? Okay, so I'm going to move a little more quickly on this one because I think we're getting the hang of these now. How many ways can the books be arranged? There are 8 books in total, random order. It's 8 times 7 times 6, etc. It's 8 factorial. Okay, the maths books must be arranged together. Think of the maths books, they are one unit. The maths books are all together. And then I've got a science book and a science book and a science book. So a group of maths books, science, science, science. How many things am I arranging? 4. How many ways can I arrange 4 things? 4 factorial. The maths books, there are 5 of them. How many ways can I arrange those 5 maths books? 5 factorial ways. So 4 factorial, because it's a group of maths, a science, a science, a science. 5 factorial, because within the maths, I can swap my order in all different ways. What about this one? The maths books must be together, the science books must be together. So I think of the maths books as a unit, the science books as a unit. How many ways can I arrange these 2 units? 2 factorial. The factorial is important because if it's not 2, then it makes a huge difference. So I can arrange the group of maths books and the group of science books in 2 factorial ways. But the maths books themselves can arrange in 5 factorial ways. The science books themselves can arrange in 3 factorial ways. And there I get my answer. Okay, question number 19. 7 blue cards, 3 green cards, 5 red cards, 2 black cards. Each card is different. How many ways can these be arranged in a straight line so that the cards of the same color are next to each other. And again, I'm taking exactly the same question, just putting a slightly different scenario to it, just so that our learners can practice more and more of these questions before I start throwing in the curveballs that are going to come in. Okay, so I've got a group of blue cards, group of green cards, group of red cards, group of black cards. I need to arrange them so cards are the same color next to each other. So how many groups have I got? 4. Blue cards, green cards, red cards, black cards. How many ways can I arrange 4 things? 4 factorial. But the blue cards themselves can be arranged in all different orders. That's where the 7 factorial comes in. The green cards, 3 factorial. Red cards, 5 factorial. Black cards, 2 factorial. Whoops, sorry, I clicked the button. Huge number. Massive, 174 million different ways. But it's the same principle as all the other ones I've done. Whoa, here comes a word. Now I'm getting repeated letters. So consider the word isosceles. In how many ways can you arrange the letters? Okay, so I've got 9 letters, so it's 9 factorial. Simple. Why am I doing this in this level where I've done so many other questions before? Why is it not the same? Well, the problem is I've got 3 S's. I've got 2 E's. So that's going to cause us a problem. If that S were blue and this were green and this were red, then a blue S, green S, red S is a different order to a blue S, red S, green S, is a different order to green, red, blue, green, blue, red, which is different. And I can't remember what I haven't done. Red, blue, green, red, green, blue, whatever. But they're not colored letters. It's the same S. So what do I have to do to my 9 factorial? I have to divide it by 3 factorial. Why 3? Because there are 3 S's. I also have to divide it by 2 factorial because there are 2 E's. So we take 9 factorial, which is the number of letters in the word. Okay, so it's 9 factorial. But the duplicates, I can't count twice or 3 times or whatever. So that's why there's 3 S's. I divide by 3 factorial, because how many ways can I arrange 3 S's in 3 factorial ways? I also divide by 2 factorial, because in how many ways can I arrange 2 E's? 2 factorial ways. Okay. Question 21. A 4-digit code is made from the digits 0 to 6. How many 4-digit codes can be made if the code has to be greater than 2,000, less than 3,000, and must be even? You may not repeat digits. So now suddenly I'm getting a question like I had before, but now I can't repeat digits, okay? And I've got from 0 to 6, which is 7 digits, and it must be even. So I've taken it and I've just raised the level a little bit. Okay, let's have a look. 4-digit code, 4 slots. What does it have to begin with? Well, it's greater than 2,000, less than 3,000, so I cannot start with a 3. So it must start with a 2. So there's only one possible digit in the first slot. It must be even. So what are my even digits? 0, 2, 4, 6, 8. I can't use 8 because they said I had to use digits 0 to 6. I can't use 2 because they said I couldn't repeat digits. So the last digit has to be a 0, a 4, or a 6. So there are 3 possibilities. How many digits did I have in total? 0, 1, 2, 3, 4, 5, 6. I've got 7 of them. I've used a 2 in the beginning. I've used one of these at the end, which means I'm left with 5 possible digits. So there are 5 there, 4 there, because whatever I use here cannot be used here. So there's question 21. Okay, so it's just taken it and just raised the level a little bit to what we've been doing. Question 22. 7 different shirts, 4 pairs of trousers hanging in a cupboard. In how many ways can the clothes be hung if all the shirts must be together and all the trousers must be together? Okay, so this is starting to sound familiar. What is the probability, not how many ways, that a shirt will hang at the beginning of the rail and a pair of trousers at the end of the rail? Okay, so 7 shirts, shirts must be together, trousers must be together. I think we're getting it now. Shirts are a group, trousers are a group. How many ways can I arrange 2 groups? 2 factorial. But the trousers themselves, there's 7 of them, sorry, shirts. Shirts can be arranged in 7 factorial ways. The trousers, there are 4 of them, they can be arranged in 4 factorial ways. Okay. What's the probability that a shirt will hang at the beginning of the rail, pair of trousers at the end of a rail? Probability, well, the total number of ways I can arrange 11 things is 11 factorial. How many successful ways can I do it? Well, if a shirt must be at the beginning, then I must have 7 things in the beginning. Okay, so there's 7 choices. Trousers at the end, so there are 4 possibilities. So I've got a shirt in the beginning, 7 options. Trousers at the end, 4 options. How many clothes have I got left? Then 9 of them, because I've got 1 here and 1 here. How many ways can I arrange the 9 in the middle? It's 9 factorial. And probability is that times that, which gives me there. Which, as we said, 11 factorial can be written as 11 times 10 times 9 factorial. And I think you can see what's going to happen here. Because what's the probability of a shirt in the beginning? There's 7 shirts over 11 items of clothing. So 7 over 11 that a shirt will be in the beginning. Trousers, there are 4 trousers. How many clothes are left once the shirt is at the beginning? 10. Same answer. We've ranked up. We're on the platinum level. This is the 5th level. As my son would very excitedly, he comes out of his room and he says, I'm in the top 50% in the world because I've now got myself halfway. And he gets very excited. Maybe we also should get very excited. Okay, question 23. Consider the word million. We've got duplicate letters again. Determine the number of 7-letter words that can be made. We've done one like that, so that's fine. Determine the probability that the vowels will be next to each other. Okay. So there's 7 letters. How many ways can you arrange 7 letters? 7 factorial. We've done lots of them. There are 2 I's. There are 2 L's. So what do I have to do, like we did with isosceles? I have to divide by 2 factorial for the I's and another 2 factorial for the L's. Determine the probability that the vowels will be next to each other. Okay, I've got I, O. So there are 3 vowels, which I think of as one group. Then there is M, L, L, O, sorry, not O, N. So it's the 3 vowels, M, L, L, N. How many things am I arranging? 5. The vowels, M, L, L, N. So I'm arranging 5 factorial things. The 3 vowels, that group of vowels, can be arranged in 3 factorial ways. But I got a curveball here because there are 2 I's still, which means I must divide by 2 factorial. There are 2 L's still, which means I must divide by 2 factorial. So not only am I thinking of the vowels as a group and then the others separately and having to rearrange these vowels, I've also got to remember they're duplicate letters, so I've got to take out the fact that I'm having the same words when the letters, because it's not a blue L and a red L, they're the same L. And then the probability that the vowels will be next to each other, well, what I've got now is that thing divided by the total number. And this one, I don't have a fancy way of doing it any other way. I don't know if there is a fancy way of doing it any other way, but I don't have a way of doing it other than using counting principles. Number 24, calculator. Again, I've got repeated letters. How many different word arrangements can be made? Determine the probability that a word arrangement starts and ends with a C. Okay, 10 letters, 10 factorial. I've got 2 C's. I divide by 2 factorial. I've got 2 A's. I divide by 2 factorial. I've got 2 L's. I divide by 2 factorial. Because I'm a pessimist, that's 6 letters. I just check. There's still a U and a T and an O and a R. Yes, there are 4 other letters that haven't been duplicated. And there I get the number of different arrangements. Probability that it starts and ends with a C. Okay, I've got 2 C's. If I think of my slots, how many C's can go in the first slot? 2. How many C's can go in the second slot? 1. How many letters are left to arrange? 8. And how many ways can I arrange them? 8 factorial. But divide by 2 factorial for the double C. Divide by 2 factorial for the double A. Divide by 2 factorial for the double L. And there I get my answer. The question said probability. So it's the number of successful ways divided by the total number of ways. Okay. Here's my sneaky way. What's the chance that it starts with a C? Well, how many C's are there? 2. How many letters are there? 10. So what's the chance that it starts with a C? 2 over 10. What's the chance that it ends with a C? Well, how many C's are left if I've got a C at the beginning? There's only 1 C left. How many letters are left if I've got a C at the beginning? Well, there are only 9 of them left. Same answer. So I don't know. Which one's better? I don't know. Whichever way. As I say, I usually do it twice just to check myself. And we are now at the emerald level. This is the 6th level. So I've done simple examples. I haven't done all codes and all letters and all people. I've done a bit of each. Straightforward examples. Take it up a notch, up a notch, up a notch, up a notch. And I actually think this might be a better way of doing it. So I'd be interested in feedback once you've taught this, if it worked. If it didn't work, I'd be very interested in feedback. Okay, question 25. Are people going to the movie? We often get questions like this. So 6 friends want to go to a movie. They will sit next to each other in a straight row. Temba and Lena haven't had an argument and refuse to sit next to each other. So this is no longer you want the vowels next to each other or the maths books next to each other. You want these two. They flatly refuse to sit next to each other. How many possible seating arrangements are there? Okay, it would be, I think, pretty impossible to try and work out how many arrangements if they flatly refuse to sit next to each other. So what we do is we work out how many ways they can sit next to each other and minus it from the number of ways they can all sit in random. So the number of ways if they sit together. So you think of Temba and Lena as one group. Then it's another 4 friends. So Temba and Lena is one group, 4 other friends. So there are 5 things I'm arranging. So that's where I get my 5 factorial. Times 2 factorial, because Temba and Lena can sit either way. The total number of ways that 6 friends can watch a movie is 6 factorial. So how do you get the number of possible seating arrangements? It's the total number minus the number if they do sit together, and that will give you that answer. Okay, so if you want people not sitting next to each other or not together, you get the number of ways they can sit together subtracted from the total number of ways, and it's much easier. It was like on Tuesday, I think it was you wanted at least 1 6 on rolling a dice 4 times. So you got rolling it no 6s and subtract. Question 26. This was from DBE 2012. Suppose a 5-digit pin can be made up by selecting digits at random and that the digits can be repeated. What is the probability that such a pin will contain at least 1 9? give your answer correct to 2 decimal places. Okay, at least 1 9. So it's a 5-digit pin. So I could have 1 9 or 2 9s or 3 9s or 4 9s or 5 9s, and there's no ways I'm going to be able to work that out. So what do? I get the number of ways that the pin contains no 9s, and I subtract. So the total number of pins, it said digits can be repeated. It's a 5-digit pin. How many numbers can I have in the first place? 10, 10, 10, 10, 10. So the total number of pins is 10 to the power 5. How many pins contain no 9s? Okay, so this means I can't use a 9, but I can still use 0, 1, 2, 3, 4, 5, 6, 7, 8. So there are 9 numbers I can use. So it's 9 to the power 5 because I can repeat digits. So how many pins must contain at least 1 9? It's the total number of 9s minus the number of pins containing no 9s. Sorry, total number of pins minus the pins containing no 9s. But the question didn't even ask that. It asked what's the probability, which means I need to keep going. So it's that answer divided by the total number of pins. So there's question 26. We're getting there. We're getting there. Okay. So this is now my 7th level. This is my hardest level, except for the 8th level, which is just some fun things that I just want to show you. Okay. And I'm afraid with this level, there are a lot of questions that are from provincial papers or DBE papers. Take a deep breath. We've got this far. We're doing well. We really, really are doing well. Okay. Question 27. A photograph is to be taken in a straight line of the 11 players in a football team. There's a captain in grade 12, a vice captain in grade 12, 5 other players in grade 12, and 4 players in grade 11. In how many ways can they be positioned if the captain may not be at either end? Okay. For a different photo, the captain and the vice captain must sit on the 5th and the 7th chair in any order. Determine the probability that the grade 11 player will sit in the first chair and a grade 12 player will sit on the last chair. Okay, let's take it slowly. In how many ways can they be positioned if the captain may not be at either end? Right, I've got 11 players. The captain may not be in the first position. So how many people can sit in that first chair? 10. The captain may not be in the last chair, but the person who's sitting in the first chair can't also be in the last chair. So how many people can sit in that last chair? 9, because it can't be the captain and it can't be whoever's in the first chair. So now how many people can sit in these remaining 9 chairs? It's 9 factorial. So it's 10 in the first chair, 9 factorial in all of these chairs, 9 in the last chair. You can also do a double negative. How many ways can these people all be seated? Any order is 11 factorial. If you put the captain at either end, in how many ways can you do it? You can get it that way as well and subtract. So you can do it also with a double negative. Okay, 27.2. The captain and the vice captain must sit on the 5th and 7th chair in any order. They have to sit there. That's fixed. Now you're going to determine some probability. So captain and vice captain must sit on the 5th and 7th chair. Fixed. Can't change that. So they're my 11 chairs. How many can go on the 5th chair? 2. It's either the captain or the vice captain. How many can go on the 7th chair? 1, because whoever's on the 5th chair obviously can't sit in the 7th chair as well. Let's keep building up. A grade 11 player will sit in the first chair. Well, if I go back here, I've got 4 grade 11 players. So how many people can sit in the first chair? 4. A grade 12 player will sit in the last chair. Okay, I've got 5 other grade 12 players. So there's 5. So this is captain or vice captain. This is the other one. This is a grade 11 on the first chair. This is a grade 12 on the last chair. So I've fixed 4 people. How many are left in this team? 7. How can I arrange them? 7 times 6 times 5 times 4 times 3 times 2 times 1. So the number of ways, that's my grade 11. These are just random players. There's my captain, vice captain, random player, the other one of captain, vice captain, random players, and my grade 12. What is the total number of ways? Now, I said the captain and the vice captain have to be on those chairs. So my total number of ways is 2 times 1, okay, because they have to be on those chairs. How many players can I arrange on the remaining 9 chairs? It's 9 factorial. And my probability is that over that. The simpler way, maybe. What's the chance of the grade 11 sitting on the first chair? There were 4 grade 11s. How many players, well, there are 11 in the team, but the captain and the vice captain have to be on those 2 chairs, the 5th and the 7th. So how many players could be sitting on that last chair? 9, because it's not the captain or the vice captain. Grade 12 on the end, so there are 5 grade 12s. How many players are left? 8, because I've got 1 sitting on the first chair, and I can't have captain or vice captain. Same answer. Question 28. Okay, in a certain province, and this was Eastern Cape, September 21, I said to you, it's at this level that they're asking these questions. In a certain province, vehicle number plates have the following format: 3 letters followed by 3 digits. These represent a letter of the alphabet, and those are a digit from 1 to 9. For each number plate that is assigned to a vehicle, the following conditions must be met. Okay, so they can't make it nice and simple for us. They've got to put curveballs in. All letters except E, G, and O can be used, and no letter can be repeated. No number plate code can start with a vowel. Okay, so that's A, E, I, O, U. But they've made it even more complicated because here's an E and an O, so I've got some letters there, and then I've got some vowels, and any digits may be used, and each digit may be repeated. Okay, that's quite cool. So the digits are 0 to 9, and they may be repeated. I'm happy about that. How many vehicles can be assigned a number plate code according to the system? Secondly, calculate the probability that a number plate code chosen from the number plates there at random contains only 1 vowel and ends with an even digit. Okay, let's go slowly. How many vehicles can be assigned a number plate code according to the system? Right, there are 6 slots. The last bits are easy. I can use all digits and each digit can be repeated. So the last bit is easy, 10, 10, 10. And I actually tend to start with that because I think, okay, I don't need to worry about that. Now, I've got 26 letters in an alphabet. I cannot use these 3, which means there are only 23 letters available to me. A number plate code cannot start with a vowel. Okay, no number plate code can start with a vowel. My remaining vowels are A, I, and U. Okay, so my remaining vowels are A, I, and U. So 23 letters in the alphabet because of that condition, minus 3 because I can't start with a vowel. So how many letters can I start with? 20. How many letters can go here? Well, there's nothing about A, I, and U with my second and third ones. So I had 23 letters in the alphabet. 1 has been used already in the beginning. which means I can only have 22 left because I cannot repeat letters. And then I cannot repeat the first letter or the second letter, so they're 21. Okay, tough. That part was fine. This part, you've just got to get your head around with the vowels and all that. Okay, I've repeated the conditions, so that's nothing new. I just repeated them so that I've got them. Calculate the probability that a number plate chosen contains only one vowel and ends with an even digit. So now they've made the even digit, which was nice. They've now gone and made it complicated as well. Okay, but let's actually start with the digits because it's not too bad. I can use any digit and they can be repeated. So it's 10 times 10, even digits, 0, 2, 4, 6, 8. So that's a 5 on the end. So that's cool. That's okay. I can handle that. You can't have a vowel in the first position. Why not? Because no number plate can start with a vowel. They wanted to contain only one vowel. So like I did with the previous question, I take the vowel in the second position. I take the vowel in the third position. If a vowel's in the second position, I can only have 3 there. A, E, I, O, U are my vowels. I can't have E, I can't have O, which means there are only 3 vowels. 26 letters in the alphabet, excluding E, G, and O is 23. Excluding my remaining vowels is 20, because I can have only one vowel. So there are 20 options there. I can't repeat letters, so there are 19 there. If the vowel's in the third position, it's exactly the same scenario. The 3 now goes in the third position. It's still 20 letters, 19 letters. And they wanted probability. It's both of these options added, divided by the total I had. And there's my answer. Okay. We're getting there. We're almost at the end. I promise. There are 2 questions, and then I just want to show you some fun questions, cool questions. Because these ones are more scary than cool, as far as I'm concerned. Okay, question 2019, DBE, June 2021, reality, it's been asked. A 3-digit number is made up by using 3 randomly selected digits from 0 to 9. No digit may be repeated. Determine the total number of possible 3-digit numbers greater than 100 that can be formed. Determine the total number of possible 3-digit numbers, both even and greater than 600, that can be formed. Okay. Right. 3-digit numbers. I'm using all the digits, so I've got 10 digits at my disposal. Okay. No digits may be repeated. I want numbers greater than 100. So in my first slot, how many options do I have? Well, 0 to 9 is 10 digits, but I can't start with a 0 because it must be bigger than 100. So there are only 9 possibilities there because I can't start with a 0. My second digit, I can't repeat digits. So now I had 10 digits. I've used one of them in the beginning. So how many are left? 9. I had 10 digits. I used one in the beginning, one in the second slot. How many left? 8. So there's my answer. The next one, determine the total number of possible 3-digit numbers, both even and bigger than 600 that can be formed. Okay, so I decided that it might be easier to do it if you start with a 6, because it's got to be bigger than 600. If you start with a 7, if you start with an 8, if you start with a 9. If you start with a 6, how many numbers can go in the beginning? 1, the 6. This has to be even. So what does it have to end in? 0, 2, 4, 6, 8. But I can't repeat. So it can't end in 6, which means how many numbers can I have at the end? 4. because I can't end it in 6 because I started it with 6. I had 10 digits to start off with. I've used a 6 in the beginning. I've used a different even number at the end. So how many digits are left for the middle one? 8, because I can't repeat. If it starts with a 7, I've got 1 in the beginning, a 7. How many can go at the end to make it even? Well, 0, 2, 4, 6, 8. I'm not repeating. So there are 5 possibilities. How many in the middle? 8. Because I can't repeat the 7 in the beginning and the even at the end. What about if it starts with 8? 1 for the 8 in the beginning, 4 for the end, because it's 0, 2, 4, 6. Whoops, sorry, I clicked while I was doing that. 0, 2, 4, 6, so it's 4 at the end, 8 in the middle. And the 9, 1 for the 9, 0, 2, 4, 6, 8 for the end. Now you can do it a little bit differently in that you can say if it starts with a 6 or an 8, then it would be 2 times 8 times 4. If it starts with a 7 or a 9, then it's 2 times 8 times 5. But for me, I just find this easier to do if it's a 6, if it's a 7, if it's an 8, if it's a 9. And it doesn't take a long time. So I understand it better than doing 6 or 8, yeah, because then I'm not duplicating that. So I personally just find that better. This is my last question, I promise. Northwest, September 2021. For those who wrote the Northwest paper in September 2021. Yo, I thought this was a tough one. Okay. There are a huge number of words, which is, I think, also part of the problem. So I'm going to try and summarize it quickly because we're going to start running out of time. You've got an athletics association. There are 12 athletes, and they're going to run the 100-meter sprint. That's irrelevant. You've got 5 provinces. You've got 2 athletes from Northwest, 3 Gauteng, 2 Limpopo, 3 Mpumalanga, 2 from Free State. No athlete had the same personal best time. Okay, there are 12 lanes next to each other in the stadium. First question, if the 12 athletes are placed according to their personal best times from fastest to slowest in lane 1 to 12, independent of the province they represent, in how many ways can the athletes be placed? Okay, so there are 12 lanes. I can't do 12 with my fingers, but there are 12 lanes. There are 12 athletes. They're placing them. Lane 1 is the fastest. Lane 2 is the next fastest, next fastest, next fastest. Okay, how many athletes can go in lane 1? 1, the fastest. How many can go in lane 2? 1, the next fastest. How many in lane 3? 1, the next fastest. How many in lane 4? 1, 1, 1, 1. In how many ways can the athletes be placed? Only 1, because they're going in order of their times. So there's only 1 way. So you sort of think 12 athletes, 12 factorial, cool. Read the question carefully, because it's not. I will confess, when I did this, I did 12 factorial. When I looked at the answers and saw it was 1, I thought, okay, you idiot, you didn't read. So read the question carefully. 30.2. The organizers of the event decide not to place the athletes according to their PBs, but to place the athlete's name in a container and select an athlete for each lane randomly. How many ways can they be placed so that the A athlete from Mpumalanga and the A athlete from Gauteng will not run next to each other? So even at part 2, we don't have them running together, which we're comfortable with. We've now got them running apart. So what we do is we consider those 2 athletes running together, get the number of ways, and then subtract. So let's, in the interest of time, and obviously you can get these slides, you can get the recording, you can do it in your own time. Okay, total number of arrangements. There are 12 athletes, 12 factorial. Number of arrangements with the 2 athletes next to each other. We've done enough examples with that now. So there are 12 athletes. 2 of them must be together. So you think of them as a 1. They are a unit. So how many things am I arranging? I'm arranging that unit plus 10 other athletes. So I'm arranging 11 things. So it's 11 factorial. But the A athlete from Mpumalanga and the A athlete from Gauteng can arrange in 2 factorial ways. So how many ways will they not run next to each other? It's 12 factorial minus that answer. 399 million ways. It's insane. Okay, 30.3. In how many ways can the athletes be placed randomly next to each other if the 2 C athletes must run in the 2 outside lanes, 1 and 12, and the A and B athletes must alternate? So not only do I have the C athletes in the outside lanes, but A and B must now alternate, and they don't tell me if it's A, B, A, B, or B, A, B, A. So like, seriously? Okay. Let's go slowly. Slots. I know 12 is a lot to write down, but I think in difficult questions it's worth it because you might then be able to get it. The 2 C athletes must run in the 2 outside lanes, 1 and 12. So how many options are there in that first lane? 2. One of the C athletes or the other one. How many options in the last lane? 1, because I've got one of them in the beginning and one of them at the end. So 2 possibilities there. One of them's already in that lane, so there's 1 possibility there. The A's and B's must alternate. So it could be A, B, A, B, A, B, A, B, A, B. How many A athletes are there? 5. Because there were 5 provinces. Okay, if we just go back here, there are 5 athletes, there are 5 B athletes. So there are 5 A athletes, 5 B athletes. Then 4, 4, 3, 3, 2, 2, 1, 1. But it could be lane 2 doesn't have to be an A athlete. It can be a B athlete. So B, A, B, A. And again, it's 5 B athletes, 5 A athletes, 4 B, 4 A, and so on. So what have I got? I've got 2 times 5 times 5 times 4 times 4 times 3 times 3 times 2 times 2 times 1 times 1 times 1. And again, exactly the same. So in the interest of space, I just did times 2 on the end there. And there you get your answer. Last question. At the end of the event, a fun run is held where only 6 athletes of the 12 are allowed to run. If the 6 athletes are chosen randomly, what is the probability that there will be exactly 1 athlete from Free State competing in the fun run? Okay, if Free State goes in lane 1, how many Free States were there? There were 2. Okay, so there are 2 Free State athletes. So there are 2 possibilities in lane 1. Free State is not allowed another one, exactly 1 athlete. So how many athletes can go in lane 2? 10, because there are 10 left from the other 4 provinces. Then 9, then 8, then 7, then 6. Why am I stopping it there? Because the fun run, only 6 athletes are allowed to run. But the Free State athlete could be in lane 2. So it could be 10 times 2 times 9 times 8 times 7 times 6. But the Free State could be in lane 3. So it could be 10 times 9 times 2 times 8 times 7 times 6. But Free State could be in lane 4 or lane 5 or lane 6. So the number of ways is 2 times 10 times 9 times 8 times 7 times 6 times 6. Because it could be in lane 1, 2, 3, 4, 5, or 6. The total number of ways these athletes can be, there are 12 athletes in the first lane, 11, 10, 9, 8, 7. Probability, you divide. And from these absolute massive numbers, you actually get a reasonable fraction, which is not bad. What about if you try and do it with probability? Okay, I think this one's quite complicated, but we'll see. If Free State is in lane 1, how many Free State people are there? 2 out of 12 athletes. So Free State's in lane 1, 2 out of 12. People in lane 2, there are 10 athletes, because I can't use the other Free State, out of 11 athletes. Then 9 out of 10, 8 out of 9, 7 out of 8, 6 out of 7. But Free State could be in lane 2 or 3 or 4 or 5 or 6, which means it's 1 over 11 times 6. Okay, tough. Right, the challenge at the beginning, for those of you who didn't join us before the time, the question was, consider the letters A, H, M, S, T. If all 5 letters are used and all the possible arrangements that can be formed are placed in alphabetical order, in which position is the word maths? Okay, so you've got to know your alphabetical order quite well. So what you do is you say, fine, words beginning with A. So if it starts with an A, okay, so A has to be at the beginning. How many letters can go in the next slot? 4, H, M, S, or T. How many letters in the next slot? 3, then 2, then 1. So how many words start with A? 24. Alphabetical order. What's the next letter in the alphabet out of A, H, M, S, T? And I very nicely gave it to you in alphabetical order, is H. How many words start with H? Again, 24. Now we take words starting with M. Okay, and that's where I want to get to. So if I start with M, I'm now left with A, H, S, T. I've got to get them in alphabetical order. You've got to know your alphabetical order quite well. So it's A, H, S, T or A, H, T, S. Okay, so that's A, H. Then I keep the A. I've used H. What's the next alphabetical order is S. Alphabetically must then be H, then T. Then it's M-A-S, then T and H. Keep M-A, which is the next one in alphabetical order is T, and I'm left with the H and the S, which is the word I want. So it's 48, 49, 50, 51, 52, 53. It's in the 53rd position. That's quite cool. And that's the end of my counting principles. But this is a game. We're going to get to master's level. This is my 8th level. We're now in the top, I don't know, 1% in the world. You know, question 1.3 in any paper 1, where they always ask a curveball that kind of relates to all sorts of weird things. Well, how about these 3 questions as a possibility? Simplify. 2023 factorial plus 2022 factorial over 2024 factorial. I said nothing about a calculator because incidentally the calculator only goes up to 69 factorial. 2023 factorial, it will just have a breakdown and won't do anything. So why can't we ask this in question 1.3? They know about factorials from counting principles, and this just uses algebra. So what do? Okay, we take out a common factor. Because what does 2023 factorial mean? It's 2023 times 2022 times 2021, etc., which is 2022 factorial. So if we take out 2022 factorial, we're left with 2023 plus 1. That gives me 2024. If I write out 2024 factorial, I can start writing it out and then leave a factorial there. How cool is this? Those cancel, and look at what my answer is. I think that's quite cool for a question 1.3. But that's not the only cool question I've got for you, sorry. Huh? What? Given 3 factorial over 3 factorial equals a times b factorial, where a and b are positive integers and b is as large as possible, determine the value of a and b. You have to be insane. Yeah, well, probably I am insane. I used to tell my boys these were cool questions, and some of them would immediately take pen and paper and try and do them because they said they knew when I said they were cool, then they knew that they would also find them cool, and the rest of the class would just look at each other and raise their eyes and just say, mad woman again. So let's take it. What is 3 factorial? It's 6. That's easy. What is 6 factorial? 720. That's not difficult either. 720 factorial, forget it. I'm not going to do it. I can't do it. A calculator can't do it. I'm not going to do it. But let's look at what we've got so far. So 3 factorial is 6. 6 factorial is 720. 3 factorial on the bottom is 6. Now, they haven't said to me, give an answer. They've said, write it in this form. How can I change 720 factorial? I can write it as 720 times 719 factorial. Now, what do you know about 6 and 720? Well, 6 goes into 720 120 times. They wanted it a times b factorial, where b is as large as possible. And then they said, determine the value of a plus b, 120 plus 729. I think it's cool. And I think it's a possible level 4 question in question 1.3. I got one more, and then I'll stop. I'll let you just have a look at that. So we've got sigma notation and factorial. Seriously? Yeah, I think I've lost it. Okay, so let's have a look at it. Sigma notation, write it out. I goes from 1, so it's 1 factorial, 2 factorial, 3 factorial, 4 factorial, all the way to 2023 factorial. 1 factorial is 1, 2 factorial, 2, 3 is 6, 4, 24, 520, no idea. 1 squared, 2 squared, 6 squared. I've got a calculator, so this isn't a problem. 24 squared, 124 squared, not a problem, but you should be able to do that in your head because 12 squared is 144 and then the 2 noughts. The question didn't say what's the answer. It said what's the units digit. Now my problem is all these dots because I've got a lot of terms. But 5 factorial is 120. It ends in a naught. 6 factorial is going to be 120 times 6. Well, if 120 ends in a naught, when I times it by 6, it will end in a naught. Happens to be 720. When I times 720 by 7, the next one, 720 ends in a naught, times by 7, it ends in a naught. In other words, all of these terms here, what are they ending in? Zeros. And the question said, what's the units digit? So my units digit will be from 1 plus 4 plus 6 plus 6 plus naught plus naught plus naught plus naught plus naught plus naught. Well, if I take 1 plus 4 plus 6 plus 6, I get 17. What is the units digit? 7. So there's I think, a super cool question.
If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from the Answer Series, your key to exam success.